In this video, we're going to review the separation of variables method. The separation of variables method, also called the separable method. So I would like to recommend that you watch the direct integration method video before you study this one, because like in that video we talk about the basic tricks that we normally use to do certain problems quickly, and then you can find the link in the description. Okay, so let's talk about how to use the separation of variable method. So let's say we have a differential equation which is dy over dx equal a function of x and y. So we have function of x and y. So the major assumption that we're gonna do is we assume that this is like a big assumption. We assume that this function can be written as a product of um, x and y. So that means this is equal to fx and gy. So you can separate them. That's why we call it separable. You separate into x and y. So this is like a if. So it's not always given. So it's like a big if there. Okay, so if this is the case, actually you can solve this equation really easy. So before we do that, let's try to understand which are separable and which are not. So let's try to do this problem first. So this is the question. So which of the following are separable? So let's look at these four. So we have dy over dx equal xy, and it is clearly see that it's already separable. It's already a product of x and y. So let's look at the next one. So we have dy over dx equal xy plus x. So it's like a sum, but you can see that if you factor x out, because you can see that you can pull x out. So if you pull x out, you can write this one as y plus 1. And then now you can see that it is a product of x function and a y function. So yes, so it is also separable. So let's look at the next one. So next we have dy over dx equal x plus y. And you can see that there's no way you can write this as a product. So it's x plus y. And actually this is like interesting problem that we solved in another video about linear first order. So we're going to come back to this problem again. So you can see that, so this one is not separable. So we can use the technique that we're trying to use here. So let's look at the other one. So we have dy over dx equal e to the x plus y. And you can see this is very similar to the previous term, x plus y. But even though this is the case, this is actually separable. The reason is, we know that using algebra, you can write this one as a product. You can break this down as e to the x times e to the y. Now when you do that, and then you can see it is a product. So it's an x term and a y term. So it is a separable equation. So you have to do some algebra sometimes just to bring it to the right form. So this is like a kind of basic. So this is what we do. Okay, now let's talk about how to actually solve this equation. So we have dy over dx equal fx times gy. So what we can do, as the title says, is separable. We're going to separate the two variables to two sides. So how we do it? First, we're going to divide by gx both sides. We assume that gy actually gy. We assume that gy not equal to 0. So we assume that under that assumption, what we do, so assuming gy not equal to 0, we can divide both sides by gy. So when you do that, you can see you can get dy over gy, and then on the other side, what we do, we're going to bring dx to the other side. We're going to bring dx to the other side. So we can write this one as fx times dx. Now what we do, we're going to integrate both sides separately. So we integrate both sides, and then you can see you get the solution now. After we do that, you can find a function of y on the left side, function of x on the other side. So this is the main formula to use for separation of variable technique. So it's not that difficult. You divide, you bring the gy to the other side, or divide, and then dx to the other side, and then integrate. Now what we do after we do that, if possible, we try to write y as a function of x. So if possible, we write y as a function of x. Sometimes this you cannot do that. So we can leave, in that case, we can leave the y as an implicit function. So implicit solution. Okay, so let's try to look at few examples now. So use the separation of variables method to solve. So actually separation of variable is like after the direct integration, this is the most common one. And you can see that the direct integration is also a subcase of a separation of variable method. But we just remember that as a different one because that's like a most common one. Yeah. So this is a separate. So direct integration is a subcase of the separation of variable method. Okay. So let's look at the first example. So we have dy over dx equal xy along with y0 equal 3. So that's the initial condition. So this is the initial condition that we normally use at the end, even though we call it the initial condition. Okay. So let's go step by step. So the first step is you separate variables. That's step 1. So separating variable, for that what we can do, we're going to move y terms to the other side. That means we divide by y. So we can say dy over y equal x dx. That's the first step. So separate the variables. And then the next step is we can integrate both sides. That's a step 2. So we integrate both sides. And then if possible, we can continue because sometimes like you get some integral that you cannot do. But in this case, actually, these are easy to integrate. So let's do that next. So for the first one, you know that this is the natural log. So it's an absolute value. And don't forget the absolute sign. And then on the other side, this is by the power rule x squared over 2 plus c. Okay, in this case, you can see that you can add a c to both sides. And then, but even if you add c to both sides, and you can see that you can simply bring one c to the other side. And because of that, we only add a c to one side. Because you can always bring c, the two c's to one side. So that means, so we just add only one. You don't want to add c1 and c2. This c is actually, if you add c1, c2, this c means c1 minus c2. Okay, or c2 minus c1. Okay, so that's what. And then what we do, we can isolate y. So after we do that, we say if possible, solve for y. And in this case, actually, you can see that you can actually solve for y. So what we do next, we can write this one using exponential, because it's a log function, using exponential function. Remember this argument. So what we know that if you have a ln a equal b, that means here you can see the base is e. So the base is e. So this means that, so how it works? So it works from e to b, b to a. So that's how it goes. So that means this simply means e to the b equal a. So please remember that. So it's going to go back and forth. So they are equivalent. The exponential form and the log form. So you go, arrow goes like that. And because of that, you can see in the next line, you can see absolute value of y equal e to the, and whatever on this side. So that means e to the x squared divided by 2 plus c. That's the next step. And then what we do, we can use some algebra here. And you can see that you can write this as a product. So you can write this one as, because we know this algebra result. So we have here a x plus y, you know that this is equal to ax ay. And because of that algebra result, we can write this one as e to the x squared over 2 and then e to the c. So we can write it like that. And then you can see that we still didn't remove the absolute sign. So we're going to remove the absolute sign. But when you remove the absolute sign, what will happen? You get the plus or minus. So when you remove the absolute sign, it's going to be plus or minus. I'm going to write the EC first for a reason. And then we write e to the x squared over 2. And you can see this the argument is this one. Because when you have, like, let's say x equal 2, absolute x equal 2, that means x equal plus or minus 2. So that's the argument. So there are two things. Okay, now you can see that e to the c plus or minus is just a number, just a constant. And because of that, I'm going to call that constant as a, just a. So we say this one is A. So, and then you can write the final answer as simply A e to the x squared over 2. So that is the general solution with a unknown A. So we normally call these a family of curves, and you can see that depending on A value, you get different solutions. So it's called a family of curves depending on A. So if you graph them, this is what happens. So you can simply graph those family. So it is e to the x squared over 2. So x squared over 2 is the function go like this on both sides, and then depending on a value, so you get different curves. So that's the family you're talking about. So you get curves like that. And if a negative, if a 0, you get 0. If a negative, you get the other side. So those are the kind of curves you get for different a values. Okay, that's a family here, family of curves. Okay, so now out of this family, maybe there's a one solution that passed through 0, passed through the initial condition, but the initial condition is 0, 3. So let's say this one. So that's the 3. If this is 3, then you can see this is 0, 3. So that's the one. So we're going to find that solution. Okay, so that's the last step. So that's step number 3. So what we do, use the initial condition, in this case y 0 equal 3 now. Okay, so if you do that, then you can see that 3, so you can say a e to the 0, you plug in x equals 0, equal 3. So this says that a equal 3, so that means your final solution you can write as y equal 3 e to the x squared over 2. So that is the solution of the initial value problem. These are what we normally call the initial value problem, because its initial value is given. So that's the final answer for this one. So let's look at a couple of more solutions, a couple of more problems. So as the next one, we have dy by over dx equal x divided by y with the condition y0 equal -2. So be careful, it's -2. So let's see what happened with the negative sign. So again, as before, separating variables and integrating. So we have, so first we're going to bring y to the other side. That means it's going to be y dy. And then we're going to move dx to the other side. It's going to be x dx. And then we're going to integrate. And then you can see the first one is going to give you y squared over 2. On the other side, going to give you x squared over 2 plus just one c. So you can just call it c1. And then what we do, we're going to multiply the whole equation by 2. We get y squared equal x squared plus 2c1. What we're going to do, just for simplicity, the 2c1 we're just going to call c, because it doesn't really matter. So we get x squared plus c. Now that's the solution. So this is what we call a implicit solution. Implicit solution. So this gives y as an implicit solution. Okay, now what we normally say, if possible, try to solve for y. Actually, in this case, you can do that because you can take the square root of both sides. So let's do that. So if you solve for y, and you can see that because the square root is square, you get y equal plus or minus. There are two different solutions, which is square root of x squared plus c. So that is the explicit solution. You write y as a function of x, but there are two solutions. Now we're gonna think about what's gonna happen here. But you know that remember the initial condition, which was negative. So we can say since y0 equal -2, which is a negative number, we select the negative solution. So we select y equal negative x squared plus c. Because the square root always give you the positive solution. When you write the square root sign, that means a positive solution or the zero solution, positive or zero. So if you want to especially say negative, then you have to put the negative sign in front. So that's what you get. Now what we do, we're going to find the c. So we can use the initial condition now. So we use the initial condition, which is y0 equal -2. So you get -2 equal negative, and you plug in x is 0 squared plus c. And then what we can do, we can solve for c. We can square both sides. When you square both sides, you get -2 squared. And then on the other side, you get c. So c equal 4 in this case. Okay, so therefore, you can have the solution like this. So the solution is y equal negative x squared plus 4 square root. So that is the solution. And you can see how we use the initial condition to pick the appropriate solution. Okay, so it's not like two solutions, it's only one solution, but that's the only one that passed through the initial condition. Okay, so let's look at the next one. So we have dy over dx equal y over x along with y1 equal to. So rewriting and integrating, we have as before dy over y this side, the other side dx over x. Oh, it's interesting. And then we can integrate both sides. So the first one going to give you ln absolute value of y. If you don't write absolute value sign, it's wrong because you lose half of the solution. And on the other side also x ln absolute value of x plus c. That's what you get. And then what we can do now, how we solve? We do like interesting argument here. We're gonna bring the log term to the other side. So you also need to know how to do the algebra here. So we can write this one as ln y minus ln x equals c, and then you know that from algebra you know that you can combine these two. We recall this result. We know that if you have log, any log, so it doesn't matter, any log, any base, so I'm going to write the base here, x minus log y is equals to log same base x over y. So that's the idea. And if you have a sum, which is the product, so because of that, you can write this one as ln. You can combine them, y over x absolute value equals c. So that's what you get. Now what we do as before, in one of the previous examples, you can write the exponential form. That means this tell you that it is y over x equal e to the c. You can write it like that. And then we can remove the absolute sign. So when you remove the absolute sign, you get plus or minus c. So you can, so next one, what we can do is we can write this one as y over x equal plus or minus e to the c. Now you can see the plus or minus e to the c is just a number. So we just call this number is a. So if you do that, then you can write this one as y over x equal a. If you multiply, then you can write finally the answer as y equal ax. So that is the final answer for this one. And then what we do, we can use the initial condition now. So let's use the initial condition. So if you use the initial condition, which says that if you plug in 1, you should get 2. So by the initial condition, so from the initial condition, you can write this one as 2 equal a times 1. That means a equal 2. So because of that, your final answer is going to be y equal 2x. So that's the final answer for this one. And you can see it's like turned out really easy and really well. So but we use some special algebra here. And then you can see this is the general solution. And this is the particular solution, special solution that satisfies the initial condition. So that's how we solve the problem. So let's look at the next one. So we have dy over dx equal xy plus x. And remember at the beginning we said that this, even though this looks like a sum, you can actually pull x out as a factor. So you can get y plus 1. So it is separable because you can separate the two. So you have to do that first. And then we're going to move the terms around. So rewriting and integrating, we can write dy over y plus 1 equal x dx, and then we can integrate both sides. And then how we do this one, and sometimes you may think that you have to use the substitution here. Actually, yeah, you can do that, but you really don't need that. So let's say if you have y plus 1, there's something interesting happen. Because when you take the derivative, you can see that it is du over dy equal 1 in this case because of the y term. That means du equal dy, and this happen every time you have a constant. So it doesn't really matter what constants you have. You can, so because of that, you can actually simply avoid the substitution part. You can just simply treat this one as just y, because that's exactly what happened here, because it's du equal dy. So using that argument, you can simply write the answer. It is ln y plus 1 absolute. We just put that. And on the other side, you get x squared over 2 by the power rule, and just add the constant. And then as we did before in previous example, we can write this one as y plus 1 equal, you can see you're going to bring it to the e first and then separate the two variables and put also plus or minus. So it's a plus or minus and e to the c, e to the x squared over 2. From the previous example we did that. And then again we can take this one as a, just a constant. So we can write this one as a e x squared over 2 and then bring 1 to the other side. So that means y equal a e x squared over 2 minus 1. So if you have an initial condition, I use it right now to find a. Otherwise, we just leave this as a general solution. So it's a general solution or family of curves. Okay, so let's look at the next one. So we have dy over dx equal e x minus 2y. And again, it looks like a sum here, but you know that you can write this one as e to the x times e to the negative 2y as a product. Now you can see it is separable because you break into a product of x and y. So now again dividing and integrating, we can, so when you divide by e to the negative 2y, because the negative sign is comes to the numerator as a positive one. That means it's going to be e to y dy. On the other side you get ex dx. And we're going to integrate these two, and for that we're going to use the familiar results, and we know that if you integrate e to a constant x, and we know that this result is going to give you, simply you divide by that constant e to the kx plus c. So that's like a very common result, but it only works when you have a k constant. Okay, so because of that, you can write the first one as 1/2 e to the 2y from the left side. From the right side it is ex, so it is ex again, and plus a constant, so we can call that constant c1 for a reason. And then we can multiply both sides by 2. So when you do that, you're going to get e to the 2y equal 2ex plus 2c1, and you can say the 2c1 for simplicity just call c. So it is 2ex plus c. Now what we can do, so we done as an implicit solution, we done here as implicit solution, but you know, if possible you should solve for y, so we can do that here. What we do, we can use this result from algebra. So you know that if you take ln of ex, you get the x term back. It's work for any x. And then the other one, if you have e to the ln x, which is going to give you x also, but this only works when x is positive. So we have those two results. Those are really important results when you want to simplify certain expressions. So we can use the first one. That means we can take ln of both sides. So if you take ln, you can say ln e to the 2y. On the other side also ln. And if you don't know if you don't know that this one is positive, then you have to take absolute value sign, because we don't know what's the sign of c. So it will be better to take absolute sign here. So absolute value 2ex plus c, because we don't know the c. If c is positive, you don't need that. Okay, so we get that. And then you can see here uh, L and E terms. L and E term get cancelled out. So that means you get 2y here. So which is 2y equal, you can see ln absolute value of 2 e to the x plus c. Now what we do, we divide by 2 both sides, and we can write the solution like this. And also we know from algebra, if you have a number like that, you can actually bring that as a power. So you can bring this as a power. So that means you can write the final answer like this. So it is simply going to be ln, you get the 2 e to the ex plus c, the absolute value and the square root. So that is the final answer, like a general solution for this problem. And if you know the initial conditions, you can use them to find c. Okay, that's how we do it. So let's look at the next one. So let's do a trigonometric one now. So we do like different types. So let's do a trigonometric one. Let's say we have cosine x dy over dx equal tan y. Again, we're going to separate the two variables, but here we're going to assume that cosine x and tan y not equal to 0. So we assume that and then divide. So assuming cosine x not equal to 0, tan y not equal to 0, and then divide. So you can write it like this now. So you can see it is 1 over tan y dy over dx. Actually, we can move the dy term to the other side. So we can simply write it like this. So dy, and the other side you're going to get 1 over cosine x dx. Now from trigonometry we know that 1 over tan means cotan. So you can write this one as cotangent. Cotangent y dy, and the 1 over cosine means secant, so it's a secant x dx. Okay, now what we do, we can integrate both sides. Okay, now what you have to do, you have to just integrate this one, and so these are like common integrals. And if you are not familiar with those common integrals, you can find a link in the description which tell you like how all those like special ones that you need to remember as a calculus or differential equation student who take in those classes, because those are like common things that you need to know. So you can find the link in the description for common antiderivatives. Okay, if you do that, and you can see that the cotangent is actually natural log sine x, sine y in this case. So it is going to be ln, you can say sine y. Because if you, what's the reason? If you take the derivative of this one, and you can see what happened, function goes down, that's a sine y, and the derivative goes to the top. That's how you take a derivative of a log function. Function goes down, and you can see this is simply the cotangent. This cotangent y. This is equal to cotangent y. This one is cotangent y. So that's the reason why this works. And similarly, for secant x, this is like you normally learn in Calc 2. So this is simply natural log secant tan. Secant x plus tan x. So these things actually you need to remember to solve problems quickly. Because you don't have time to like derive these from problems in an exam or quiz or somewhere. But you can do that in a homework, but not in those places, or time restricted. Okay, and then again you add the c. Now the goal is to, if possible, so this is an implicit solution, so perfectly fine as an implicit solution. But what we normally do, we see whether we can actually simplify this a little bit. So actually we can, because this is a e, this is ln, so you can bring it to one side. We did a similar problem earlier. We bring it to one side and write as a fraction first, and then do the exponential form. So that you can do. Oh, there's another easy way. What you do, you raise the whole equation to an e term. So like what I'm talking about is this. So let's say you have like a equal b. So if you have a equal b, you can raise this one e to the a equal e to the b. So we do that idea. But here things are much better, because the reason is we have ln, we have ln term. So that means we have ln A equal ln B kind of situation. So I mean when you raise to the E, when you raise to the E, what happen? You can actually cancel this ELN term using the result that we just discussed in the previous example. So you get A equal B. So we can use that argument here. So we raise the equation to E or whatever the base. So in this case is ln, so E. So you get A equal B. So we can do that. So that means if you're raising this whole equation to the base E, so you can write this one, the whole equation as E to ln and then E to this. So because of that, now ELN and ELN get cancelled out in both sides. So what happens is you get other expressions that you have. So this says that simply sine y absolute value equal secant x plus tan x plus c. Actually, there's like a slight typo here. You don't, when you do that, actually you get, because E also need to raise to, the plus C also need to raise to E. So there's an E term there. So that means what will happen, you don't get a plus C here. So you get times E to the C. That's what you get. And then what you do, you remove the absolute sign. So when you remove the absolute sign, and you can see that you're going to get sine y equal, again, plus or minus. So the plus or minus comes here. So we can put the plus or minus to this one. And then we can call this whole thing as A. This whole thing as A. That means you can write the final answer as A times secant x plus tan x. Really nice algebra here. So that's the general solution. So this is the implicit solution of the problem. The implicit solution is sine y equal A times secant x plus tan x. So we have to solve up to this one. And then also if the initial conditions are given, then you can also solve for A. And also if you want, you can actually completely solve taking inverse of both sides. You can write the solution as sine inverse. So y equals sine inverse of this. So you can also do that step. So final solution you can write as a y equals sine inverse A times secant x plus tan x. Okay, so let's look at the next one. So let's look at a different type of problem. So we have dy over dx equal y squared minus 4, and it's clearly you can see that this is a separable equation, because in this case the x function is just 1. So that's why it's not appeared, because you can multiply this one by 1. So this is still a separable equation. So let's say you want to find all the solutions. If you want to find all the solutions, so you will notice that you first need to find what they call the constant solutions. You get a constant solution if you can find a y that satisfies both sides, and you can clearly see that if you set this the right hand side to 0, you get y equal plus or minus 2. So since y equal plus or minus 2, if you take the derivative, you can see that dy over dx is 0 because it's just a constant. So you can see y equal plus or minus 2. When you plug in that, the right hand side is clearly 0, but if you take the derivative, because the constant, and you can see it's also 0. That means you get 0 equals 0, both sides. That means y equal plus or minus 2 are solutions. So we can write that first. So we notice that first. So you can say first notice that y equal plus or minus 2 are solutions. Are solutions. It satisfies the equations. Are solutions, or what we normally call the constant solutions. But still there's a question, like for example, let's say you are given a initial condition. Let's say your initial condition is y 0 equal 3 or something else, something other than this. Then these are not solutions because it doesn't satisfy the condition. But in generally, these two are solutions. So if there are no initial conditions given and you can see it doesn't satisfy because there's no condition to check, so you get y equal plus or minus 2 as solutions. So depending on the problem. But if you are given some other conditions like y0 equal 1 or y0 equal 3, something like that, then those two are not solutions of the problem. But in generally, these two are solutions. And then after that, we can assume that y not equal to those two. Okay, so we can assume, and then after that we say assuming. So this is actually how to clearly, like, completely solve these problems. Assuming y not equal to any of them, you can divide, and dividing, so you can divide the whole equation, and then you can write this one as dy over y squared minus 4 equal on the other side dx, just dx, and then we can integrate. So the question is, right hand side you can integrate, which is just x plus c. So that part is done. But the problem is how to do the left side, how to do the right side. For the right side, actually you have to use the partial fraction method. So we can use a partial fraction method for that. Or you can use a shortcut, because if you remember a formula, so that's a formula. So you can use that, in specific, if you know that, because this is like it's a character 2 result. So if you remember this formula, what it says, if you have dx over x squared minus a squared, if you integrate this one, this is actually going to give you ln, so 1 over 2a, so we have 1 over 2a, and then ln, you get x minus a, and then x plus a. So you can use this result in exams, especially for differential equation classes. You can't, I don't think you can do that in Calc 2, because there you would need to show the work. But in advanced classes, you can actually directly use this result. And there's another result. So we also have dx over x squared plus a squared. If you have plus sign, which is the arctan or tan inverse, so 1 over a tan inverse x over a. But here we need this one. So what we do, let's use the partial fractions for this one, and then you will see that you end up with the same answer. So using partial fractions, so we can write the decomposition like this. And we know that y squared minus 4 has two factors, y minus 2 and y plus 2. So this is y minus 2 and y plus 2. Because of that, you can directly write it like this. And which is identically equal to, make that you write 3 lines, because we use properties of identities here. So you can write equal sign here. It's like a logically incorrect. So it's a over the first factor, and then b over the second factor. And the goal is to find a and b. And then if you remember, there's like a shortcut again, they call the cover-up method. Cover-up method actually going to give you these values really quickly. So what's the cover-up method is, we're going to cover up this factor in the original one and then plug in the 0 of this one. So in this case, 0 is y equal 2. So if you plug in y equal 2 here, and you can see you get 4. That means the a is 1/4. So that's like what they call cover-up method. So it's a 1/4 y minus 2. And similarly, to find b, we remove this term of the original one. We're going to cover up this one, and for the rest of them, we're going to plug in the 0. 0 is in this case negative 2. So if you do that, you get negative 1/4. So that means that here you get negative 1/4 over y plus 2. Okay, so that's how you use cover-up method. But let's try to use a regular method. So you can use any method you like. So it's a cover-up method. And if you need to know more about that, I have already provided the link in the description to learn more examples with some different tricks. Okay, so let's use the regular technique just to show you. So there are 3 ways to get it. First one is the formula, second is the cover-up method, or this one. So what we normally do, we're going to multiply both sides by this factor. That's like normally what we do. And you can see, so you get 1 equal on the other side a, the other factor. You get y plus 2 here. And then b, you get y minus 2. You always get the other one. Okay, now what we do, we're going to use substitution. That's the quickest way to get this one. So you can see if you substitute the other 0 to find a, you plug in the 0 of the other term. That's the idea. So you plug in y equals 2. So if you do that, and you can see you get 1 equal a, 2 plus 2 is going to give you a equal 1/4. We already know this one from the cover-up method. And you get the same answer. And then again, you're going to substitute y equal -2. You get 1 equal b now. -2, -2 is going to give you the b value, which is, you can see, -1/4. All those like nicely comes here. Okay, so that's how you do it normally. And then we're going to plug in that into the integral, and you normally like pull 1/4 out. We write, but that's just a number. We pull that out and we can write it like this. So we can plug in like this, and then you can see, you can easily find the integral of those two. So that is, first one is going to give you 1/4 ln y minus 2 epsilon. We talk about this one. When you have constant, you can just simply treat this one as y. We discussed this one. And minus, again 1/4, same thing. It is simply ln y plus 2. You don't need any substitution here, because if you take the derivative, it's just 0. And then you can add a c. You can do that at the end. Okay, now what we can do, you can actually combine them. It's a minus sign. That means you're going to divide these two. So you can write it like this. So it's 1/4 ln first one divided by the second one. And don't forget the absolute sign. So that's what you get. And you can see that this also you can get from the formula we just discussed. Remember the formula? So you can get the same result from this formula also. So you are okay to use that. And you can see in this case a equal 2. If you put a equal 2, you get 2a, which is 1/4, and y minus 2, y plus 2, that's exactly what we have here. Okay, so okay, let's say either way, you have 3 ways to do it: the cover-up method, or the regular partial fraction method, or the formula. So somehow you get this one. Now your goal is to, let's plug in this one in our problem now. So this is just the integral. So we have this one now. So by substituting, we get this. On the other side, we have x plus c. And next what we do, we're going to multiply by 4 to cancel this out. So you can write it like this. Now what we can do, we can write the exponential form. So we write the exponential form, and also remove the absolute sign because we did it multiple times. So you can see it is y minus 2 over y plus 2, which is equals to plus or minus. You can write this one as e to the 4x times e to the 4c. You can write it like that. You know this algebra now. Now what we do, you can see you can combine not those two. You can combine these two. You can combine this with the plus or minus sign. You can combine all of them, and you can just call it a. So if you do that, you can write this one as a e to the 4x. Okay, now your goal is to, actually you can call, yeah, so we normally use c, so you can say c, that's fine. So any letter, but this c is different from the previous one, so it's just c. Those two c's are not the same. Okay, so you can write it like that, just a c, just a constant. And then you can solve for y. How to solve for y? What we normally do, we're going to do the cross multiplication. We're going to multiply by these both sides. So when you do that, you can see you can write this one as y minus 2 equal, if you multiply by y plus 2, on the other side you're going to get cy e to the 4c, that's the first term, and then 2c e to the 4x. Now what we're going to do, we're going to bring y terms to one side. So if you bring all the y terms to one side, this one and that one, and factor out y, you can write it like this. So 1 minus ce4x. If you move 2 to the other side, it is 2. You can factor out. You're going to get 1 plus ce4x. Now what we do, we divide by this factor both sides. So I to isolate y. So you can write y like this. So y equal, and then you can see 2 is a factor. and you can write this one as 1 plus CE4x divided by 1 minus CE4x. So that is the general solution. So this is how you get the general solution after a lot of algebra. Now let's consider a few cases. So you can see when C equals 0, if you just plug in C equals 0, you can see that you get y equal 2. And that is one of the solutions we talked about at the beginning, the y equal. So that means y equal 2 solution is already near. So you get that for C equals 0. And then let's see something else. And then also, if you divide this whole equation by 4x, you can divide this expression, the top and bottom, by 4x, e to the 4x. You can divide by this term. So then what happened? You can see dividing by e to the 4x. So you can write the solution like this. So you can say it is equal to y 2 times, you say e to the negative 4x plus c, and e to the negative 4x minus c. That's what you get. And then let's see what happens when x goes to infinity. So if you send x to infinity, and you can see that these two terms become 0. So these two terms become 0. So you get c over minus c, which is negative 1. So you get y equal negative 2. The other solution like this. So when x goes to infinity, e to the negative 4x goes to 0. Thus y goes to negative 2. But the solution actually cannot be obtained for any value of c. It doesn't matter what value you plug in, you cannot get this solution, y equal negative 2 solution. So those kind of solutions are what we normally call singular solutions. So those kind of solutions are what we call singular solution. So that means there's a one singular solution, y equal negative 2, and there's a general solution. That means we can write the final answer like this. So y equal negative 2, that's one solution, and the other solution is y equal 2 times 1 plus c e to the 4x divided by 1 minus c e to the 4x, where c is a constant. So that's how we write the complete solution problem like that, because sometimes we actually skip one solution, y equal negative 2. That solution you cannot get from the other general solution. Okay, so let's look at the next one. So as the next one, let's look at this very interesting problem, and you can see here it's like looks like complicated. And so again, what we need to do is we need to bring the y terms to one side, and you can see there are y terms on the other side as well, and also we need to bring x terms to the other side. So to do that, what we can do, we can divide first by ex by ey both sides, and also divide both sides by tan x, assuming all the conditions that are not equal to 0. So let's do that. Or we can simply say separating variables. Separating variables, we have e to the 3y minus y divided by ey and sine 2x divided by tan x dx. And then what we do next is we can integrate, but before that actually you can see some algebra here. Actually you can see from the trigonometric identity, sine 2x equals to 2 sine x cosine x. That's the trigonometric identity. And also tan is sine over cosine. So this is sine x over cosine x. And because of that, you can see the tan x get cancelled out. So after we do that, you simply gonna get 2 sine x. Sine x term actually get cancelled out. So you get 2 cosine is squared because there's a cosine term that can come to the top. So that means finally we have this. This is going to be 2 cosine squared x dx. That's what you get. Now we can integrate those both sides. So we can write it like this. And also on the left side, you can see you can divide by ey. So if you divide by ey, you're going to get e to the 2y minus y e negative y if you bring all the terms to the numerator, and the dy. That's what on this side. On the other side, what we have is 2 cosine squared x dx. Now we can integrate both sides. So how to integrate? And you can see the first one you can use is a constant. So simply divide by that. So that means it's going to be 1/2 e to the 2y, the first term. The second term, you can see you have to use integration by parts. What we normally use the DI method, whereas a shortcut, you can get the answer quickly. And on the other side, you can see you have to use the double angle formula here. And we know this result. So we know that uh, cosine squared x equal 1 plus cosine 2x divided by 2. So we can use that result for the second one. So we can write this one as integral of 1 plus cosine 2x, because there's like a 2.5, so we can cancel out. So that's what you get. And then yeah, and then you know how to integrate the second one. That's not that difficult. And then what you want to do is we have to use the DI method for the you can also use a regular integration by parts, but DI would be much quicker. So let's have the DI and get the answer. So we use a DI for the second one. So what do you do? We write y and then e to the minus y. So take the derivative, take the integral, take the derivative, take the integral until you get a 0, and then we get a 0. So then we multiply across the diagonal starting with plus sign. That's the idea. And then we multiply them across the diagonal. So that means we're gonna get the answer to the first two. So first one we have 1/2 e to the 2y. Second one, with this negative sign and the negative sign we get, it becomes plus. So the first one is going to give you y e negative y. That's what, because you just multiply across the diagonal. And the second one also going to be minus, with the minus sign going to plus e to the minus y. That's what happened on the left side. For the right side, 1 means x, and the cosine means sine, and then we divide by 2. So it's going to give you 1/2 sine 2x plus a constant. Next what we do, we can multiply the whole equation. So this is the implicit solution. So this is perfectly fine if you need the implicit solution. But if you need the like a little better one, actually what we can do much here, but we can do little things. So for example, we can multiply this one by 2, and also you can multiply the whole equation by 2 and ey, because that simplifies this a little bit. So if you multiply by 2ey, you're gonna get e to the 3y. That's the first one. Next you get y. Next you get 1, because you multiply by, actually there's a 2 also, you forgot the 2. So you get 2y plus 2, and on the other side you get ey, and then 2x, 1/2 get cancelled out, so you get sine 2x, and plus 2c. Those 2c we can just call it c, it doesn't matter, we just need a number there. Okay, so that's what you get. So this is much better than the previous one, I mean a little bit better. Now we use the initial condition. So use the initial condition, and we see that y0 equals 0. So that means you plug in wherever you see x0, and also y0. So if you do that, you get 1 plus 2 on this side. On the other side you get c. So this is c is 3. So c equal 3. So now we can plug in that. So so thus the implicit solution is e to the 3y plus 2y plus 2 equal e to the y 2x plus sine 2x plus 3. So that is the implicit solution of the equation. Okay, so let's do the next one. Next, actually, we can look at a differently formatted problem. So let's see this one. So we have 3 plus x dy minus y squared dx, and you can see that this is not in the standard form, or what we call the normal form. So what we can do, we can still do the separation. We can just divide by 3 plus x and y squared, and first actually we can move y squared dx down to the other side and then divide. So we can write it like this. So separating variables, first you have 3 plus x equals to y squared dx, and then we divide. So we can write it like this. And integrating, now how to integrate the left side? And left side you have 1 over y squared. When 1 over y squared you can write as y to the negative 2. Now we can use the power rule. So power rule, you subtract, you add 1 divided by that. So it's become negative 1 over y. So we can write it like that. So I mean this side is negative 1 over y. On the other side is, we already talk about this one. If you have a constant, you can simply treat this one like x. So it's 1 over x. So that means you're going to get ln 3 plus x and then plus c. And then what we can do is we can multiply by the negative sign and flip over. So you can write the solution like this. So this is the general solutions for the problem. Okay, so let's look at another one. You remember the population dynamics problem, population growth and decay problems. Actually, population growth and decay are also separable, like nice example for a separable equation. The population growth and decay models, population growth and decay models. And we know that those formula have a common format. You know that all those formulas you can write as dp, if you see the population size p, over dt, which is normally equals proportional to the p, the population size, and that's going to give you the differential equation dp over dt equal k proportional constant times p. So that is the format of a population dynamic problem. And depending on the sign of k, you get two different cases. So if k is positive, you get what they call the population growth model. So it's going to go like that, starting with the value. And if k negative, you get the decay. So the decay model. So starting with p naught is going to decay. So both have the same formula. One is k positive, one is k negative. Okay, so let's see how we can solve this one. And you can see this is also a really nice example for a separable method. So you can divide by p both sides. You can write this one as dp over p equal k dt, and then so this is separable, and then we're gonna take the derivative both sides, integral both sides. So if you do that, you can see here you get ln absolute p, the other side you get kt plus c, and then we're gonna bring it to the exponential form and remove the absolute sign. So we do all of them, remember quickly. So you're gonna write this one as e to the kt plus c. We did a lot of time, it's the same thing. So this we write ec e to the kt and remove the absolute sign. So you get plus or minus e to the c e to the kt, and then we simply consider this one as just a constant. So that means your solution is a e k t. So that's how we solve it. And then use the initial condition. So using the initial condition p0 equal p naught, so some value at the beginning, there's some value. So and then you can plug in. So that means so you can say that it's going to give you p naught equal a e to the 0. E to the 0 is 1. So this says that a equal p naught. So that means finally you can write the population model as pt equal initial value e to the kt. If k positive is going to grow, if k negative is going to decay. It's the same formula. Okay, So that's how we solve the population growth model using the separation of variable method. Okay, let's try to do one more very interesting problem. It looks like a little hard, but it's like a really nice argument how we can actually simplify really well. So let's do this one. Uh, Suppose we have 1 plus y squared dx plus 1 plus x squared dy. And then, so you can see this is separable clearly. So separating variables and integrating, we have this. Now, actually, how to integrate this one? We can recall this result from Calc 2. So we know that the integral of 1 over 1 plus x squared is 1 over a tan inverse x over a. Tan inverse means sometimes some people write arctan. It's the same thing. Yeah, so we can use that to both sides. So that means we can write the right side, left side is simply tan inverse y. The other side is minus tan inverse x plus c. If you bring both terms to one side, we can write this one as tan inverse y plus tan inverse x equals c. So this is the implicit solution. So you can see it's give us implicit solution. But actually you can simplify this really nicely. So we have the first implicit solution. So we have the implicit solution. But you can actually use a trigonometric identity to simplify this really well, and we can even find an explicit solution. So let's see how we can do that. So using this trigonometric identity, we know this one. Tan a plus b equals to tan a plus tan b divided by 1 minus tan a tan b. So this is a trigonometric identity. Now what we can do, we are going to use, we can look at our formula solution what we have. So we're going to call the first term a because this is an angle. So we're going to call a, the second one we're going to call b, and we're going to substitute. So this is what we get. We're going to actually substitute the right side first. So we have tan inverse y plus tan inverse b, tan inverse x actually, not b, tan inverse x, and then in the bottom 1 minus tan inverse y, tan inverse x equal, you have tan a plus b. A plus b is c, so you get tan c. Tan c is just a number. You can say just c, but they are not the same c. So you can say c1 just for clarity. Okay. So and then also you can see so these get cancelled out, and then you simply get y plus x over 1 minus xy equals c, and then and you can see it's really nicely simplified, and also you can actually isolate y. If you cross multiply and bring all the terms to one side, we can do this. So we have y plus c equals c minus cxy. Now what we do, we're going to bring the y terms to one side and factor out and divide, so we get the final answer like this. It should be y plus x on this one. Okay. So you get y equals c minus x over 1 plus cx as the final answer for this one. Okay, now let's try to do two theoretical problems just for completeness. So we have this problem. So let's see what happens if you have like a general problem like that. Dy over dx equals some function of fx, and then yx not equal y naught. And you can see that this is clearly separable again. So what we do, so we're gonna separate the two variables like this. So separating and integrating from x naught to x. Separating and integrating from x naught to x. So we do from x naught because it's given, and then we pick a general x. So that's the interesting part. So if you do that, so what do you get? So we have dy on this side, so we can separate this. So when you separate, you're gonna get fx dx, and then integrate from x naught to x. And when you do that, on the other side you get y naught to y. Those are the corresponding values. And then you can see on the left side you get y minus y naught, because the integral is just y. On the other side there's nothing you can do, we just leave it like that. So it is x naught x fx dx, because it's a theoretical problem. And then we move y naught to the other side, so you can finally write your solution as y naught plus x naught x fx dx. So that is how you can write a solution in general. So this is like a useful result for some other courses. We normally write it like that if you have a problem like this. So you just integrate from x naught to x. Okay, that's the idea. So let's look at one last problem. This is also very interesting. Let's look at this one. dy over dx equal e to the negative x squared, y0 equal y. And you know that this is like one of the famous integral that you famous one that you cannot integrate. So that means this is a really good one for the previous formula. So we do the same thing as we did before in the previous one. Integrating from 0 to x, we have this. So if you want to write this as an indefinite integral, then it's okay here to write it like this. But when you have the same variable here, we are not going to use the same one. We use some other variable. So let's try to use like a variable like t or something. So then we can write it like this. So here we use like a dummy variable t. So it's a t variable. And then because you are not going to use the same variable in both in the limit and the function. So that's how we write it like that. And then on the left side, actually you get y. Because we assume that y0 equals 0. And then what is on the right side? On the right side we have like a very interesting function. That's what we call the error function. So let's recall that. So there's a function called error function. So how we define the error function? It's very useful in engineering or physics applications. So what it says that, so you look at the gamma function, normalized gamma function, and then we see what is the area after 0. So this area is what we call the error function. So what is this area? How much you are away from the center or the mu. That's the mean value. So how far you are away from the mean is the error function. How much error. So we're going to define this one as the, if you call this is x, this is the error. So we call ERF, error function, x. So we write it like that. And the definition is this one. So it is simply, so error function x is defined as 2 over square root, not 2 over square root pi, 2 over square root pi, and then the integral from 0 to x e to the negative t square dt. So it's the area under the gamma function from 0 to x. So this is what we call the error function. Error function. Now actually we can use this because that's exactly what we have here. We just need to multiply by pi and divide by 2. So that means your final answer you can write as y equal square root pi divided by 2 the error function of x. So this is how we write the solution. So using the error function, because sometimes we do that when you cannot integrate certain ones. Okay, so these are the most important problems that you need to know under the separation of variable techniques. And in another video I'm going to give you some practice problems for you to try, so you can try them after you're watching this one. And this video was a little long because there were so many different types that you need to consider. And when you go to other ones, like for example linear first order and exact equation, Bernoulli, homogeneous, those are not that long. So we do like about maybe like 5 problems from those ones. But here we did a lot of problems. Okay, so thank you so much for watching.